early days was taking reality, the practice met with the perceptron, often thought of as a single layer neural network, but actually what's not as much known as Frank Rosenblatt was also the developer of the multi-layer perceptron. And that history, zooming through, has amazed our civilization. To me, one of the most inspiring things in the world of games. First with the great Garry Kasparov losing to IBM Deep Blue in 1997. Then Lee Sedol losing to AlphaGo in 2016. Seminal moments. And captivating the world through the engineering of actual real-world systems. Robots on 4 wheels, as we'll talk about today, from Waymo to Tesla to all of the autonomous vehicle companies working in the space. Robots on 2 legs, captivating the world of what actuation, what kind of manipulation can be achieved. The history of deep learning. From 1943, the initial models from neuroscience thinking about neural networks, how to model neural networks mathematically, to the creation, as I said, of the single layer and the multi-layer perceptron by Frank Rosenblatt in 1957 and 62, to the ideas of backpropagation and recurrent neural nets in the 70s and 80s, to convolutional neural networks and LSTMs and bidirectional RNNs in the 80s and 90s, to the birth of the deep learning term and the new wave, the revolution in 2006, to the ImageNet and AlexNet, the seminal moment that captivated the possibility, the imagination of the AI community of what neural networks can do in the image and natural language space, closely following years after, to the development of the popularization of GANs, generative adversarial networks, with AlphaGo and AlphaZero in 2016 and 7, and as we'll talk about, language models, transformers in 17, 18, and 19. Those have been the last few years have been dominated by the ideas of deep learning in the space of natural language processing. Okay, celebrations. This year, the Turing Award was given for deep learning. This is like deep learning has grown up and finally start giving awards. Jan LeCun, Jeffrey Hinton, Yasser Benjer received the Turing Award for the conceptual engineering breakthroughs that have made deep neural networks a critical component of computing. I would also like to add that perhaps the popularization in the face of skepticism, for those a little bit older have known the skepticism that neural networks have received throughout the 90s. In the face of that skepticism, continuing pushing, believing, and working in this field, and popularizing it through in the face of that skepticism, I think is part of the reason these 3 folks have received the award. But of course, the community that contributed to deep learning is bigger, much bigger than those 3. Many of whom might be here today at MIT, broadly, in academia and industry. Looking at the early key figures, Walter Pitts and Warren McCulloch, as I mentioned, for the computational models of the neural nets, these ideas of thinking that the kind of neural networks, biological neural networks can have on our brain can be modeled mathematically. And then the engineering of those models into actual physical and conceptual mathematical systems by Frank Rosenblatt, 57, again, single layer, multi-layer in 1962. You could say Frank Rosenblatt is the father of deep learning, the first person to really, in 62, mention the idea of multiple hidden layers in neural networks. As far as I know, somebody will correct me. But in 1965, shout out to the Soviet Union and Ukraine, the person who is considered to be the father of deep learning, Alexei Evaknenko, and V.G. Lapa, co-author of that work, is the first learning algorithms on multi-layer perceptrons, multiple hidden layers. The work on backpropagation on automatic differentiation in 1970. In 1979, convolutional neural networks were first introduced, and John Hopfield looking at recurrent neural networks, what are now called Hopfield networks, a special kind of recurrent neural networks. Okay, that's the early birth of deep learning. I want to mention this because it's been a kind of contentious space now that we can celebrate the incredible accomplishments of deep learning. Much like in reinforcement learning, in academia, credit assignment is a big problem. And the embodiment of that, almost to a point of meme, is the great Jürgen Schmidhuber. I encourage for people who are interested in the amazing contribution of the different people in the deep learning field to read his work on deep learning and neural networks. It's an overview of all the various people who have contributed besides Jan LeCun, Jeffrey Hinton, and Yoshua Benjura. It's a big, beautiful community, so full of great ideas and full of great people. My hope for this community, given the tension, as some of you might have seen, around this kind of credit assignment problem, is that we have more,
I need mom.
not on this slide, but love. There can never be enough love in the world, but general respect, open-mindedness, and collaboration and credit sharing in the community. Less derision, jealousy, and stubbornness, and silos, academic silos within institutions, within disciplines. Also, 2019 was the first time it became cool to highlight the limits of deep learning. This is the interesting moment in time. Several books, several papers have come out in the past couple of years highlighting that deep learning is not able to do the broad spectrum of tasks that we can think of the artificial intelligence system being able to do, like common sense reasoning, like building knowledge bases and so on. Rodney Brooks said by 2020, the popular press starts having stories that the era of deep learning is over.
Good to see you.
And certainly there has been echoes of that through the press, through the Twitter sphere and all that kind of world. And I'd like to say that a little skepticism, a little criticism is really good always for the community, but not too much. It's like a little spice in the soup of progress. Aside from that kind of skepticism, the growth of CVPR, iClear, NeurIPS, all these conference submission papers has grown year over year. There's been a lot of exciting research, some of which I'd like to cover today. My hope in this space of deep learning growth, celebrations, and limitations for 2020 is that there's both less hype and less anti-hype. Less tweets on how there's too much hype in AI, and more solid research. Less criticism and more doing. But again, a little criticism, a little spice is always good for the recipe. Hybrid research, less contentious, counterproductive debates, and more open-minded interdisciplinary collaboration across neuroscience, cognitive science, computer science, robotics, mathematics, physics, across all these disciplines working together. And the research topics that I would love to see more contributions to, as we'll briefly talk about in some domains, is reasoning, common sense reasoning, integrating that into the learning architecture, active learning and lifelong learning, multimodal, multitask learning, open domain conversations, so expanding the success of natural language to dialogue, to open domain dialogue and conversation, and then applications. The two most exciting, one of which we'll talk about, is medical and autonomous vehicles. Then algorithmic ethics in all of its forms, fairness, privacy, bias. There's been a lot of exciting research there. I hope that continues. Taking responsibility for the flaws in our data and the flaws in our human ethics. And then robotics. In terms of deep learning application robotics, I'd love to see a lot of development, continued development, deep reinforcement learning application in robotics, robot manipulation. By the way, there might be a little bit of time for questions at the end. If you have a really pressing question, you can ask it along the way too. Questions so far? Thank God. Okay. So first, the practical, the deep learning and deep RL frameworks. This has really been a year where the frameworks have really matured and converged towards two popular deep learning frameworks that people have used as TensorFlow and PyTorch, or TensorFlow 2.0 and PyTorch 1.3 is the most recent version. And they've converged towards each other, taking the best features, removing the weaknesses from each other. So that competition has been really fruitful in some sense for the development of the community. So on the TensorFlow side, eager execution, so imperative programming, kind of how you would program in Python has become the default, has been first integrated, made easy to use, and become the default. And on the PyTorch side, Torch script allowed for now graph representation. So do what you're used to be able to do in what used to be the default mode of operation in TensorFlow. Allow you to have this intermediate representation that's in graph form. On the TensorFlow side, just the deep Keras integration and promotion as the primary citizen, the default citizen of the API, of the way you interact with TensorFlow, allowing complete beginners, just anybody outside of machine learning, to use TensorFlow with just a few lines of code to train and do inference with the model. That's really exciting. They cleaned up the API, the documentation, and so on. And of course, maturing the JavaScript in the browser, implementation of TensorFlow, TensorFlow Lite, being able to run TensorFlow on phones, mobile, and serving. Apparently, this is something industry cares a lot about, of course, is being able to efficiently use models in the cloud. And PyTorch catching up with TPU support and experimental versions of PyTorch Mobile, so being able to run a smartphone on their side. This tense, exciting competition. Oh, and I almost forgot to mention, we have to say goodbye to our favorite Python 2. This is the year that support finally, in January 1st, 2020, support for Python 2, and TensorFlow's and PyTorch support for Python 2 has ended. So goodbye, print, goodbye, cruel world. Okay. On the reinforcement learning front, we're kind of in the same space as JavaScript libraries are in. There's no clear winners coming out. If you're a beginner in the space, the one I recommend is a fork of OpenAI baselines, is stable baselines. But there's a lot of exciting ones. Some of them are really closely built on TensorFlow. Some are built on PyTorch, of course, from Google, from Facebook, from DeepMind, Dopamine, TF Agents, TensorForce. Most of these I've used. If you have specific questions, I can answer them. So stable baselines is the OpenAI baselines fork. As I said, this implements a lot of the basic DeepRL algorithms, PPO, ITC, everything. Good documentation, and just allows very simple, minimal, few lines of code implementation of the basic, the matching of the basic algorithms of the OpenAI gym environments. That's the one I recommend. Okay, for the framework world, my hope for 2020 is framework agnostic research. So one of the things I didn't mention is PyTorch has really become almost overtaking TensorFlow in popularity in the research world. What I'd love to see is being able to develop an architecture in TensorFlow or develop it in PyTorch, which you currently can, and then once you train the model, to be able to easily transfer it to the other, from PyTorch to TensorFlow, from TensorFlow to PyTorch. Currently, it takes 3, 4, 5 hours if you know what you're doing in both languages to do that. It'd be nice if there was a very easy way to do that transfer. Then the maturing of the DeepRL frameworks. I'd love it to see OpenAI step up, DeepMind to step up, and really take some of these frameworks to maturity that we can all agree on. Much like OpenAI Gym for the environment world. And continued work that Keras has started, and many other wrappers around TensorFlow has started, of greater and greater abstraction, allowing machine learning to be used by people outside of the machine learning field. I think the powerful thing about supervised, sort of basic vanilla supervised learning is that people in biology, in chemistry, in neuroscience, in physics, in astronomy, can deal with a huge amount of data that they're working with, and without needing to learn any of the details of even Python. So that I would love to see greater and greater abstractions which empower scientists outside the field. Okay, natural language processing. 2017, 2018 was when the transformer was developed and its power was demonstrated most, especially by BERT. Achieving a lot of state-of-the-art results on a lot of language benchmarks, from sentence classification to tagging, question answering, and so on. There's hundreds of data sets and benchmarks that emerged, most of which BERT has dominated in 2018. 2019 was sort of the year that the transformer really exploded in terms of all the different variations. Again, starting from BERT, XLNet. It's very cool to use BERT in the name of your new derivative of a transformer. Roberta, distilled BERT from Hugging Face, Salesforce, OpenAI, GPT-2, of course, Albert, and Megatron from NVIDIA. Huge transformer. A few tools have emerged. So one on Hugging Face is a company and also a repository that has implemented in both PyTorch and TensorFlow a lot of these transformer-based natural language models. So that's really exciting. So most people here can just use it easily. So those are already pre-trained models. And the other exciting stuff is Sebastian Reuter, great researcher in the field of natural language processing, has put together NLP Progress, which is all the different benchmarks for all the different natural language tasks, tracking who, sort of leaderboards of who's winning where. Okay, I'll mention a few models that stand out, the work from this year. Megatron LM from NVIDIA is basically taking, I believe, the GPT-2 transformer model and just putting it on steroids, right? 8.3 versus 1.5 billion parameters. And a lot of interesting stuff there, as you would expect from NVIDIA.
Thank you.
Of course, there's always brilliant research, but also interesting aspects about how to train in a parallel way. Model and data parallelism in the training. The first breakthrough results in terms of performance, the model that replaced BERT as king of transformers is XLNet from CMU and Google Research. They combine the bidirectionality from BERT and the recurrence aspect of Transformer XL, the relative positional embeddings, and the recurrence mechanism of Transformer XL. So taking the bidirectionality and the recurrence, combining it to achieve state-of-the-art performance on 20 tasks. Albert is a recent addition from Google Research, and it reduces significantly the amount of parameters versus BERT by doing parameter sharing across the layers. And it has achieved state-of-the-art results on 12 NLP tasks, including the difficult Stanford question answering benchmark of Squad 2. And they provide open source TensorFlow implementation, including a number of ready-to-use pre-trained language models. Okay, another way for people who are completely new to this field, a bunch of apps, right? Transformer is one of them, from Hugging Face, popped up that allows you to explore the capabilities of these language models. And I think they're quite fascinating from a philosophical point of view. And this has actually been at the core of a lot of the tension of how much do these transformers actually understand, basically memorizing the statistics of the language in a self-supervised way by reading a lot of text. Is that really understanding? A lot of people say no, until it impresses us, and then everybody will say it's obvious. But right, with Transformer is a really powerful way to generate text to reveal to you how much these models really learn. Before this, yesterday, actually just came up with a bunch of prompts. So on the left is a prompt you give it. The meaning of life here, for example, is not what I think it is, it's what I do to make it. And you can do a lot of prompts of this nature. It's very profound. And some of them will be just absurd. You'll make sense of it statistically, but it'll be absurd and reveal that the model really doesn't understand the fundamentals of the prompt that's being provided. But at the same time, it's incredible what kind of text it's able to generate. The limits of deep learning, I'm just having fun with this at this point, are still in the process of being figured out. Very true. Had to type this. Most important person in the history of deep learning is probably Andrew Ng. I have to agree. So this model knows what it's doing. And I tried to get it to say something nice about me, and that took a lot of attempts. So this is kind of funny, is finally it did one. I said, Lex Freeman's best quality is that he's smart. I said, finally. But it's nothing but ever happens. But I think he gets more attention than every Twitter comment ever. And that's very true. Okay, a nice way to sort of reveal through this that the models are not able to do any kind of understanding of language is just to do prompts that show understanding of concepts and being able to reason with those concepts, common sense reasoning. Trivia 1 is doing 2 plus 2 is a 3, 5 is a 6, 7, the result is a simple equation, 4, and 2 plus 3 is, like, you got it right and then it changes its mind. Okay, 2 minus 2 is 7, so on. You can reveal any kind of reasoning. You can do it blocks, you can ask it about gravity, all those kinds of things. It shows that it doesn't understand the fundamentals of the concepts that are being reasoned about. And I'll mention of work that takes it beyond, towards that reasoning world in the next few slides. But I should also mention with this GPT-2 model, if you remember about a year ago, there was a lot of thinking about this 1.5 billion parameter model from OpenAI. It is so, the thought was it might be so powerful that it would be dangerous. And so the idea from OpenAI is when you have an AI system that you're about to release that might turn out to be dangerous, in this case used probably by Russians, fake news, for misinformation, that's the kind of thinking, is how do we release it? And I think while it turned out that the GPT-2 model is not quite so dangerous, that humans are in fact more dangerous than AI currently, that thought experiment is very interesting. They released a report on release strategies and the social impacts of language models that almost didn't get as much attention as I think it should. And it was a little bit disappointing to me how little people are worried about this kind of situation. There was more of an eye roll about, oh, these language models aren't as smart as we thought they might be. But the reality is, once they are, it's a very interesting thought experiment of how should the process go of companies and experts communicating with each other during that release. This report thinks through some of those details. My takeaway from just reading the report from this whole year of that event is that conversations on this topic are difficult because we, as the public, seem to penalize anybody trying to have that conversation. And the model of sharing privately, confidentially between ML or machine learning organizations and experts is not there. There's no incentive or a model or a history or a culture of sharing.
I can't carry anymore.
Okay. Best paper from ACL, the main conference for languages, was on the difficult task of, so we talked about language models. Now there's the task, taking it a step further, of dialogue, multi-domain, task-oriented dialogue. That's sort of like the next challenge for dialogue systems. And they've had a few ideas on how to perform dialogue state tracking across domains, achieving state-of-the-art performance on multi-WAS, which is a 5-domain, challenging, very difficult 5-domain human-to-human dialogue data set. There's a few ideas there. Should probably hurry up and start skipping stuff. On common sense reasoning, which is really interesting, is this is one of the open questions for the deep learning community, AI community in general, is how can we have hybrid systems of whether it's symbolic AI deep learning or generally common sense reasoning with learning systems. And there's been a few papers in this space. One of my favorite from Salesforce on building a data set where we can start to do question answering, figuring out the concepts that are being explored in the question and answer. Here, the question, while eating a hamburger with friends, what are people trying to do? Multiple choice. Have fun, tasty, indigestion. The idea that needs to be generated there, and that's where the language model will come in, is that usually a hamburger with friends indicates a good time. So you basically take the question, generate the common sense concept, and from that be able to determine the multiple choice, what's happening, what's the state of affairs in this particular question. Okay. Alexa Prize, again, hasn't received nearly enough attention that I think it should have. Perhaps because there hasn't been major breakthroughs, but it's open domain conversation that all of us, anybody who owns an Alexa, can participate in as a provider of data. But there's been a lot of amazing work from universities across the world on the Alexa Prize in the last couple of years, and there's been a lot of interesting lessons summarized in papers and blog posts. A few lessons from Alquist's team that I particularly like, and this is kind of echoes the work in IBM Watson with the Jeopardy challenge, is that one of the big ones is that machine learning is not an essential tool for effective conversation yet. So machine learning is useful for general chit chat when you fail at deep, meaningful conversation or actually understanding what the topic we're talking about. So throwing in chit chat and classification, sort of classifying intent, finding the entities, detecting the sentiment of the sentence. That's sort of an assistive tool. But the fundamentals of the conversation are the following. So first you have to break it apart. So the conversation is you can think of it as a long dance. And the way you have fun dancing is you break it up into a set of moves and turns and so on, and focus on that, sort of live in the moment kind of thing. So focus on small parts of the conversation, taking their time. Then also have a graph, sort of conversation is also all about tangents. So have a graph of topics, and be ready to jump context, from one context to the other and back. If you look at some of these natural language conversations that they publish, it's just all over the place in terms of topics. You jump back and forth, and that's the beauty, the humor, the wit, the fun of conversations. You jump around from topic to topic. And opinions. One of the things that natural language systems don't seem to have much is opinions. If I've learned anything, one of the simplest ways to convey intelligence is to be very opinionated about something and confident. And that's a really interesting concept about conversation. And in general, there's just a lot of lessons. Oh, and finally, of course, maximize entertainment, not information. This is true for autonomous vehicles. This is true for natural language conversation, is fun should be part of the objective function. Okay. Lots of lessons to learn there. This is really the Loebner Prize, the Turing test of our generation. I'm excited to see if there's anybody's able to solve the Alexa Prize. Again, Alexa Prize is your task with talking to a bot, and the measure of quality is the same as the Loebner Prize, is just measuring how good was that conversation, but also the task is to try to continue the conversation for 20 minutes. If you try to talk to a bot today, and you have a choice to talk to a bot or go do something else, watch Netflix, you last probably less than 10 seconds. You'll be bored. The point is to continue trapping you in the conversation because you're enjoying it so much. And the 20 minutes, that's a really nice benchmark for passing the spirit of what the Turing test stood for. Examples here from the Alexa Prize, from the Alquist bot. So the difference in two kinds of conversations. So Alquist says, have you been in Brazil? The user says, what is the population of Brazil? Alquist says, it is about 20 million. User says, well, okay. This is what happens a lot with, like I mentioned, multi-domain conversation, is once you jump to a new domain, you stay there. Once you switch context, you stay there. The reality is you want to jump back and continue jumping around. Like in the second more successful conversation, have you been in Brazil? What is the population of Brazil? It is around 20 million. Anyway, I was saying, have you been in Brazil? So you're jumping back in context. That's how conversation goes. Tangent to tangent and back. Quickly, there's been a lot of sequence-to-sequence kind of work using natural language to summarize. A lot of applications. One of them for Make Clear that I wanted to highlight from Technion that I find particularly interesting is the abstract syntax tree-based summarization of code. So modeling computer code, in this case, sadly, Java and C#, in trees, in syntax trees, and then operating on those trees to then do the summarization in text. Here, an example of a basic power of 2 function on the bottom right. In Java, the code to sec summarization says get power of 2. That's an exciting possibility of automated documentation of source code. I thought it was particularly interesting, and the future there is pretty bright. Okay, hopes for 2020 for natural language processing is reasoning, common sense reasoning becomes greater and greater part of the transformer type language model work that we see in the deep learning world. Extending the context from hundreds or thousands of words to tens of thousands of words. Being able to read entire stories and maintain the context. Which transformers, again, with XLNet, Transformer XL is starting to be able to do, but we're still far away from that long-term, lifelong maintenance of context. Dialogue, open domain dialogue, forever since Alan Turing to today is the dream of artificial intelligence, being able to pass the Turing test. And the dream of sort of natural language model transformers are self-supervised learning. And the dream of Jan LeCun is for these kinds of what previously were called unsupervised, but he's calling now self-supervised learning systems, to be able to sort of watch YouTube videos and from that direct to form representation based on which you can understand the world. Sort of the hope for 2020 and beyond is to be able to transfer some of the success of transformers to the world of visual information, the world of video, for example. DeepRL and self-play. This has been an exciting year, continues to be an exciting time for reinforcement learning in games and robotics. So first, Dota, 2, and OpenAI, an exceptionally popular competitive game, esports game that people compete, win millions of dollars with. So this is a lot of world-class professional players. So in 2018, OpenAI 5, this is a team play, tried their best at the international and lost, and said that we're looking forward to pushing 5 to the next level, which they did in April 2018. They beat the 2018 world champions in 5-on-5 play. So the key there was compute. 8 times more training compute. Because the actual compute was already maxed out, the way they achieved the 8x is in time, simply. Training for longer. So the current version of OpenAI 5, as Jacob will talk about next Friday, has consumed 800 petaflop per second days and experienced about 45,000 years of Dota self-play over 10 real-time months. Again, behind a lot of the games we're going to talk about, they use self-play, so they play against each other. This is one of the most exciting concepts in deep learning. Systems that learn by playing each other and incrementally improving in time, so starting from being terrible and getting better and better and better and better, and always being challenged by a slightly better opponent because of the natural process of self-play. That's a fascinating process. The 2019 version, the last version of OpenAI 5, has a 99.9 win rate versus the 2018 version. Okay. Then DeepMind also in parallel has been working and using self-play to solve some of these multi-agent games, which is a really difficult space when people have to collaborate as part of the competition. It's exceptionally difficult from the reinforcement learning perspective. So this is from raw pixels, solve the arena capture the flag game, Quake 3 Arena. One of the things I love, just as a sort of side note, about both OpenAI's and DeepMind and general research in reinforcement learning, there will always be 1 or 2 paragraphs of philosophy. In this case, from DeepMind, billions of people inhabit the planet, each with their own individual goals and actions, but still capable of coming together through teams, organizations, and societies in impressive displays of collective intelligence. This is a setting we call multi-agent learning. Many individual agents must act independently, yet learn to interact and cooperate with other agents. This is an immensely difficult problem because with co-adapting agents, the world is constantly changing. The fact that we, 7 billion people on Earth, people in this room, in families, in villages, can collaborate while being, for the most part, self-interested agents is fascinating. One of my hope sections for 2020 is to explore social behaviors that emerge in reinforcement learning agents and how those are echoed in real human-to-human social systems. Okay, here's some visualizations. The agents automatically figure out, as you see in other games, they figure out the concepts. So knowing very little, knowing nothing about the rules of the game, about the concepts of the game, about the strategy and the behaviors, they're able to figure it out. There's the T-SNE visualizations of the different states, important states and concepts in the game that this figures out, and so on. Skipping ahead, automatic discovery of different behaviors. This happens in all the different games we talk about, from Dota to StarCraft to Quake. The different strategies that it doesn't know about, it figures out automatically. And the really exciting work in terms of the multi-agent RL on the DeepMind side was the beating world-class players and achieving Grandmaster level in a game I do know about, which is StarCraft. In December 2018, AlphaStar beat Mana, one of the world's strongest professional StarCraft players, but that was in a very constrained environment, and it was a single race, I think Protoss. And in October 2019, AlphaStar reached Grandmaster level by doing what we humans do, so using a camera, observing the game, and playing as part of against other humans. So this is not an artificial side system. This is doing exact same process humans would undertake and achieve Grandmaster, which is the highest level. Okay, great. I encourage you to observe a lot of the interesting on their blog posts and videos of the different strategies that our RL agents are able to figure out. Here's a quote from one of the professional StarCraft players, and we see this with Alpha 02 in chess, is AlphaStar is an intriguing, unorthodox player, one with the reflexes and speed of the best pros, but strategies and style that are entirely its own. The way AlphaStar was trained with agents competing against each other in a league has resulted in gameplay that's unimaginably unusual. It really makes you question how much of StarCraft's diverse possibilities pro players have really explored. And that's the really exciting thing about reinforcement learning agent in chess, in Go, in games, and hopefully simulated systems in the future that teach experts that think they understand the dynamics of a particular game, a particular simulation, of new strategies, of new behaviors to study. That's one of the exciting applications from almost a psychology perspective that I'd love to see reinforcement learning push towards. And on the imperfect information game side, poker, in 2018, CMU, Noah Brown was able to beat head-to-head No Limit Texas Hold'em, and now Team 6 player No Limit Texas Hold'em against professional players. Many of the same results, many of the same approaches with self-play, iterative Monte Carlo, and there's a bunch of ideas in terms of the abstractions. So there's so many possibilities under the imperfect information that you have to form these bins of abstractions in both the action space in order to reduce the action space and the information abstraction space. So the probabilities of all the different hands they can possibly have and all the different hands that the betting strategies could possibly represent. And so you have to do this kind of course planning. So they use self-play to generate a course blueprint strategy that in real time they then use Monte Carlo search to adjust as they play. Again, unlike the DeepMind OpenAI approaches, very minimal compute required, and they're able to achieve to beat world-class players. Again, I like this is getting quotes from the professional players after they get beaten. So Chris Ferguson, famous World Series of Poker player, said Pluribus, that's the name of the agent, is a very hard opponent to play against. It's really hard to pin him down on any kind of hand. He's also very good at making thin value bets on the river. He's very good at extracting value out of his good hands, sort of making bets without scaring off the opponent. Darren Elias said its major strength is its ability to use mixed strategies. That's the same thing that humans try to do. It's a matter of execution for humans. To do this in a perfectly random way, to do so consistently, most people just can't. Then in the robotic space, there's been a lot of applications of reinforcement learning. One of the most exciting is the manipulation, sufficient manipulation to be able to solve the Rubik's Cube. Again, this is learned through reinforcement learning. Again, because self-plays in this context is not possible, they use automatic domain randomization, ADR, so they generate progressively more difficult environments for the hand. There's a giraffe head there, you see. There's a lot of perturbations to the system, so they mess with it a lot, and then a lot of noise injected into the system to be able to teach the hand to manipulate the cube in order to then solve. The actual solution of figuring out how to go from this particular phase to the solved cube is an obvious problem. This paper and this work is focused on the much more difficult learning to manipulate the cube. It's really exciting. Again, a little philosophy, as you would expect from OpenAI, is they have this idea of emergent meta-learning. This idea that the capacity of the neural network that's learning this manipulation is constrained, while the ADR, the automatic domain randomization, is progressively making harder and harder environment. So the capacity of the environment to be difficult is unconstrained. And because of that, there's an emergent self-optimization of the neural network to learn general concepts as opposed to memorize particular versions. The hope for me in deep reinforcement learning space for 2020 is the continued application of robotics, even sort of legged robotics, but also robotic manipulation. Human behavior, the use of multi-agent self-plays I've mentioned to explore naturally emerging social behaviors, constructing simulations of social behavior, and seeing what kind of multi-human behavior emerges in self-play context. I think that's one of the nice, I hope there'll be like a reinforcement learning self-play psychology department one day, like where you use reinforcement learning to study, to reverse engineer human behavior and study it through that way. And again, in games, I'm not sure what the big challenges that remain, but I would love to see, to me at least, it's exciting to see learned solution to games, to self-play. Science and deep learning, I would say there's been a lot of really exciting developments here that deserve their own lecture. I'll mention just a few. Here from MIT in early 2018, but it sparked a lot of interest in 2019. Follow-on work is the idea of the lottery ticket hypothesis. So this work showed that subnetworks, small subnetworks within the larger network, are the ones that are doing all the thinking. The same results in accuracy can be achieved from a small subnetwork within a neural network. And they have a very simple process of arriving at a subnetwork of randomly initializing a neural network. That's, I guess, the lottery ticket. Train the network until it converges. This is an iterative process. Prune the fraction of the network with low weights. Reset the weights of the remaining network with the original initialization, the same lottery ticket. And then train again the pruned, untrained network. And continue this iteratively, continuously, to arrive at a network that's much smaller, using the same original initializations. This is fascinating, that within these big networks, there's often a much smaller network that can achieve the same kind of accuracy. Now, practically speaking, it's unclear what are the big takeaways there, except the inspiring takeaway that there exist architectures that are much more efficient. So there's value in investing time in finding this network. Then there is a disentangled representation, which again deserves its own lecture, but here showing a 10 vector representation, and the goal is where each part of the vector can learn one particular concept about a data set. So the dream of unsupervised learning is you can learn compressed representations where every one thing is disentangled, and you can learn some fundamental concept about the underlying data that can carry from data set to data set to data set to data set. That's disentangled representation. There's theoretical work, best ICML paper in 2019 showing that that's impossible. So disentangled representations are impossible without inductive biases. And so the suggestion there is that the biases that you use should be made explicit as much as possible. The open problem is finding good inductive biases on supervised model selection that work across multiple data sets that we're actually interested in. A lot more papers, but one of the exciting is the double descent idea that's been extended and to the deep neural network context by OpenAI to explore the phenomena that as we increase the number of parameters in a neural network, the test error initially decreases, increases, and just as the model is able to fit the training set, undergoes a second descent. So decrease, increase, decrease. So there's this critical moment of time when the training set is just fit perfectly. Okay, and this is the OpenAI shows that it's applicable not just to model size, but also to training time and data set time. This is more like an open problem of why this is, trying to understand this, and how to leverage it in optimizing training dynamics in neural networks. There's a lot of really interesting theoretical questions there. So my hope there for the science of deep learning in 2020 is to continue exploring the fundamentals of model selection, training dynamics, focus on the performance of the training in terms of memory and speed worked on, and the representation characteristics with respect to architectural characteristics. So a lot of the fundamental work there in understanding neural networks. Two areas that I had pulled two sections on in papers, which is super exciting. My first love is graphs. So graph neural networks is a really exciting area of deep learning. Graph convolution neural networks, as well as solving combinatorial problems and representation systems that are really useful in any kind of problem that is fundamentally can be modeled as a graph, can be then solved or at least aided in by neural networks. There's a lot of exciting area there, and Bayesian deep learning using Bayesian neural networks, that's been for several years an exciting possibility. It's very difficult to train large Bayesian networks, but in context that you can, it's useful, small data sets. Providing uncertainty measurements in the predictions is extremely powerful capability of Bayesian neural networks, and online incremental learning of these neural networks. There's a lot of really good papers there. It's exciting. Okay, autonomous vehicles. Oh boy. Let me try to use as few sentences as possible to describe this section with a few slides. It is one of the most exciting areas of applications of AI and learning in the real world today. And I think it's the way that artificial intelligence, it is the place where artificial intelligence systems touch human beings that don't know anything about artificial intelligence the most. Hundreds of thousands, soon millions of cars will be interacting with human beings, robots, really. So this is a really exciting area and a really difficult problem. And there's two approaches. One is level 2, where the human is fundamentally responsible for the supervision of the AI system. And level 4, or at least the dream is, where the AI system is responsible for the actions and the human does not need to be a supervisor. Okay, two companies represent each of these approaches that are sort of leading the way. Waymo in October 2018, 10 million miles on road. Today, this year, they've done 20 million miles in simulation, 10 billion miles, and a lot. I got a chance to visit them out in Arizona. They're doing a lot of really exciting work, and they're obsessed with testing. So the kind of testing they're doing is incredible. 20,000 classes of structured tests, of putting the system through all kinds of tests that the engineers can think through, and that appear in the real world. And they've initiated testing on road with real consumers without a safety driver. If you don't know what that is, that means the car is truly responsible. There's no human catch. The exciting thing is that there is 700,000, 800,000 Tesla autopilot systems. That means there's these systems that are human supervised. They're using a multi-headed neural network, multitask neural network to perceive, predict, and act in this world. So that's a really exciting real-world deployment, large scale of neural networks. It's a fundamentally deep learning system. Unlike Waymo, which is deep learning is the icing on the cake. For Tesla, deep learning is the cake. Okay, it's at the core of the perception and the action that the system performs. They have to date done over 2 billion miles estimated, and that continues to quickly grow. I'll briefly mention, which I think is a super exciting idea in all applications of machine learning in the real world, which is online, so iterative learning, active learning. Andre Karpathy, who's the head of Autopilot, calls it the data engine. It's this iterative process of having a neural network, performing a task, discovering the edge cases, searching for other edge cases that are similar, and then retraining the network, annotating the edge cases and then retraining them, and continuously doing this loop. This is what every single company that's using machine learning seriously is doing. Very little publications on this space of active learning. But this is the fundamental problem of machine learning. It's not to create a brilliant neural network, it's to create a dumb neural network that continuously learns to improve until it's brilliant. And that process is especially interesting when you take it outside of single task learning. So most papers are written on single task learning. You take whatever benchmark, here in the case of driving, it's object detection, lane mark detection, drivable area, trajectory generation, right? All those have benchmarks. And you can have separate neural networks with them. That's a single task. But combining, you use a single neural network that performs all those tasks together. That's the fascinating challenge, where you're reusing parts of the neural network to learn things that are coupled and then to learn things that are completely independent, and doing the continuous active learning loop. There, inside companies, in the case of Tesla and Waymo in general, it's exciting to have people, these are actual human beings that are responsible for these particular tasks, that become experts of particular perception tasks, experts of particular planning tasks, and so on. And so the job of that expert is both to train the neural network and to discover the edge cases which maximize the improvement of the network. That's where the human expertise comes in. Okay. And there's a lot of debate, it's an open question about which kind of system would be, which kind of approach would be successful. A fundamentally learning-based approach, as is with the level 2, with the Tesla Autopilot system, that's learning all the different tasks involved with driving, and as it gets better and better and better, less and less human supervision is required. The pro of that approach is the camera-based systems have the highest resolution, so that it's very amenable to learning. But the con is that it requires a lot of data, a huge amount of data, and nobody knows how much data yet. The other con is human psychology, is the driver behavior, that the human must continue to remain vigilant. On the level 4 approach, that leverages, besides cameras and radar and so on, also leverages LiDAR and map. The pro is that it's much more consistent, reliable, explainable system. The detection, the accuracy of the detection, the depth estimation and detection of different objects is much higher, accurate with less data. The cons is it's expensive, at least for now. It's less amenable to learning methods because much fewer data, lower resolution data, and must require, at least for now, some fallback, whether that's the safety driver or teleoperation. The open questions for the deep learning level 2 Tesla Autopilot approach is how hard is driving? This is actually the open question for most disciplines in artificial intelligence. How difficult is driving? How many edge cases does driving have? Can we learn to generalize over those edge cases without solving the common sense reasoning problem? It's kind of the task, without solving the human level artificial intelligence problem. And that means perception. How hard is perception? Detection, intention modeling, human mental modeling, the trajectory prediction, and then the action side, game theoretic action side of balancing, like I mentioned, fun and enjoyability with